Good morning to one and all. So now we are about to close this particular unit, divide and conquer. So we have discussed this general method, binary set, finding min-max, mid-sort, quick-sort. All these things have been discussed so far. And we have left over with defective chessboard problem. Defective chessboard problem. And already for every algorithm, we have been measuring the performance analysis. For every algorithm, we did this one. So performance analysis for divide and conquer is being done every algorithm individually. Okay, so today I'd like to complete this defective chessboard problem. And what is this particular problem and how this problem can be solved? Is there any uses of this particular problem? So these are the 3 points we'd like to concentrate. And previously, in the previous class, we have discussed regarding to merge-sort algorithm, how merge-sort algorithm is being operated, and what is the complexity of a merge-sort algorithm, and how the complexity can be analyzed. Everything has been seen in the previous session. And today, I'd like to concentrate on defective chessboard problem. So let's get started without any further delay. Okay, performance measurement is already being done while every problem has been taken into consideration here. Okay, now let us consider here. So take the defective chessboard problem. What exactly this particular problem will be? So everybody has chessboard having approximately 8 by 8 tiles will be available within the chessboard. So totally 64 tiles will be there in the chessboard. And this problem can be specified or identified that one particular tile of entire 64 will be defective. That is not available, defective in the sense, so that may not be available, or that may not be eliminated, or that may not be considered. May not be available, may not be eliminated, or so not considered, either of these three. For example, if you consider something like this, for example, so this is the, for example, I'd like to write a very proper way here, not exactly 64 tiles. I'd like to take some number of tiles here. For example, if you have to take into consideration of this is the chessboard, and one of the tile, probably this particular tile is not supposed to be available. This is eliminated from this particular chessboard, for example. Then if it is eliminated, then you could not place any coin, any chess coin on that particular place. So that is the meaning. Why? That is why it is called as a defective chessboard problem. Okay, this is the way to identify the defective chessboard problem. So this defective tile might be available anywhere else, not exactly in the corner, anywhere else in the chessboard here. So to do this particular operation, what exactly we are trying to do, or what exactly we are trying to concentrate is, so I would like to concentrate by using divide and conquer. Always divide and conquer will be tells you or gives you that, so it could be always decompose the problem or divide the problem into further smaller problems. Therefore, so based on the problem, so the number of smaller problems will be decided. If you take min-max, so small of p will be get satisfied with the 2. If you take quick-sort, binary set, and merge-sort, the number of smaller problems will be 1. And if you take a defective chessboard problem, here also, so either it is 1 by 1 or 2 by 2, something like that. So within this particular consideration, let us get started here. So what is the actual problem here? What is the actual given conditions for the problem? Given conditions is, so you have to consider a chessboard of having size n by n is the size, and where n will be equal to 2 power k. It must be remembered by you. Where n will be, here the problem has been given, the condition has been given that n equal to 2 power k. But in remaining all other problems, we have to consider divide and conquer So basic primitive. That basic primitive is n equal to 2 power k. We have to consider in the evaluation part, and thereby we have to identify or we have to measure the performance of that particular algorithm. So using what do you call in finding complexity. But here the problem has so explicitly, externally it has been given. Okay, 2 power k into 2 power k kind of chessboard will be there. So you can replace with 2 power k by n, or n will be replaced with 2 power k. Then exactly out of these 2 power k or n, whether n will be equal to some 2 in the sense. So you do have a 2 by 2 chessboard with you, 2 by 2 chessboard. Totally, you have 4 tiles will be there within that particular chessboard. Out of these 4 tiles, exactly only one square or one tile will be defective. Will be defective. Okay, you please consider. If you take so some n will be equal to some 8 in the sense. So obviously you could consider the 8 into so 8. So probably this would be 64. Out of this 64, only one. Any number of tiles are there within the chessboard. That doesn't matter. Only one tile will be defective. Remaining everything will be gets okay, and you can place the coin over there, and you can play the game using that particular chessboard. That doesn't have any problem. But only one defective tile will be there among all those available or existed number of tiles based on the value of n. Okay, this is the second condition. And the third condition is, so you have to cover one one particular tile will be defective, and using that particular defective tile, you have to cover so with a new technical word for you, triominos. Triominos. Tri in the sense of 3, monios in the sense it could be arranged in L shape. It could be arranged in L shape. Okay, if you have 3 tiles will be there, 3 squares will be there. How can you arrange them in a triomino mode in the sense? First possibility will be this one. Second possibility will be this one. Of course, you have to rotate them. That's all. Third possibility will be so this one. Fourth possibility will be this one. Okay. So this is one kind of L. This is another kind of L, and so this is another kind of L, and this is another kind of L. You just rotate them by so 90 degree, 90 degree, 90 degree, and so on 90 degree for number of times. Then you could get this kind of L-shaped forms. Okay. Now, how could you get the solution of this? How could you? Is there any possibility to get the solution? Yes, we do. We do have a solution. So for this particular defective chessboard problem, using divide and conquer. Okay, using divide and conquer. So there is a possibility to get the solution here. So then, how could you get that particular solution or there? So let us examine. First of all, just examine. Then we'll go ahead and so discuss the complete problem. Okay. How could you get this one here in the sense? So possibility will be, so as we consider the chessboard size is n by n, so n by n, and each n by n size will be so 2 power k. Okay, it is basic assumption, not assumption, given condition actually. This is actually given condition. And if you consider this particular condition, so the total number of squares will be so 2 power k into 2 power k, that is 2 power 2k number of 2 power 2k number of so squares are there within your so what you call chessboard. And out of this 2 power 2k, how many number of defective tiles are there or defective squares are there? Only one. So therefore, remaining so very good squares which are available with you is so 2 power 2k minus 1. After deducting that particular thing, you could have this particular value. Okay, how many in the sense? So if you have total number of squares will be, sorry, total number of values will be equal to n equal to 2 in the sense. So 2 into 2, that is 4, and 1 defective in the sense. If you deduct 1 here, then you could have 3. 3 are good squares tiles, and 1 is defective. So here, if you take n equal to 8, 8 by 8 will be 64 tiles will be there, and minus 1 will be equal to 63. Okay, minus 1 will be equal to 63. Totally 63 number of so tiles which are in good position. Only one will be defective. Something like that. Number of in general formula, it could be taken into consideration like this: 2 power 2k minus 1. Okay. Then followed by whether this 2 power 2k minus 1 will be divided by 3 or not. Why we have taken this particular division by 3? What is the meaning? What is the secret behind the consideration of this particular divisible by 3 in the sense? Consider these triominos. These triominos having first tile, second tile, and third tile. If you take anything, first tile, second tile, and third tile. Okay, first tile, second tile, or third tile. First square, so second square or third square. So every triomino, whatever the angle it might be, every triomino does have 3 number of squares. It is made up of 3 number of tiles or squares. So therefore, we have to examine that whether it could be divisible by 3 or not. If it is divisible by 3, yes, you can able to cover up all other non-defective with triominos. If it is not divisible by 3, you cannot cover because 1 will be left over. 1 will be left over. And one more thing you need to remember here. So here you can consider, so here 2 power 2k, let us consider 2 power 2 into k. Whatever the value of k, so after multiplying with 2, it will become a even number. Okay, this is become an even number. Let me give you after couple of seconds. I'll give you the induction value. Okay, even value. Even value minus 1 will be always produces odd value only. Okay, 2 power 2 into 1, that is 2. 2 power 2 into 2, that is 4. 2 power 2 into 3, that is 8. 2 power 2 into 4, that is 16. So 2 power 16, let us consider 2 power 3. So 2 power 3 in the sense 8. So 8 by 8 will be 64. 64 minus 1 will be odd number. Okay. If any odd number will be there, most probable odd numbers will be divided with 3. Okay, let us taking this one here by induction. By induction, whether this could be done or not. K equal to 0. If k equal to 0 in the sense 2 power 2 into 0 minus 1. That is 1 minus 1, that is 0. So 0 could not be divisible by 0 could be divisible by any number, there is no problem. And k equal to 1. K equal to 1 in the sense actually the value of k is odd, but 2 into 1, that is 4 minus 1. 4 minus 1 equal to 3. Yes, it could be divisible by 3. If k equal to 2, 2 power 2 into 2, that is 4. 2 power 4 minus 1, that is 16 minus 1 will be equal to 15. Yes, it could be divisible by 3. And k equal to 3. 2 power 2 into 3, that is 2 power 6 minus 1, 64 minus 1. So therefore, so 64 minus 1 will be equal to 63, also divisible by 3. All these values, if you continue these values, k equal to 4, 5, 6, and so on, if you continue that one, so you could always get the resultant values which are divisible by, which could be divisible by 3. So it could be gets true. So if this particular condition will be gets true, yes, we could say you can able to cover up all other pies or squares with the triominos. It could be possible. Okay. So this is the basic problem. This could be the basic problem. Okay. So I'd like to repeat this basic problem very precisely, very precisely. You have been given n by n chessboard, and where n will be equal to, each n will be equal to 2 power k. And out of these n by n chessboard, n by n tiled chessboard, or n by n squared chessboard, you have exactly one defective square. One defective square will be defective within that particular entire chessboard. And except that particular defective chessboard, so you have to cover up using triominos. Triomino in the sense the tiles which are arranged in L shape. Okay, there are four possibilities are there to arrange that particular triomino, which has been given or shown in the diagrams over there. And this problem can be solved using divide and conquer. How this could be in the sense, we have to come up with one idea. That idea is number of tiles will be 2 power k by 2 power k. If you solve this for that one, 2 power 2k number of tiles will be there in the chessboard. Out of 2 power 2k chessboards, tiles of chessboard, one particular tile will be defective. So therefore, you have to eliminate that particular tile from the 2 power 2k. Therefore, 2 power 2k minus 1. If you take 2 power 2k minus 1, that will be always divisible by 3. It can possible. It can possible to divisible by 3. Okay, by induction, this is the value. So this is entire problem. This is entire problem. In coming slides, we are supposed to show everything by using only diagrams. Okay, at the end you have some algorithm and analysis, but everything will be shown using diagrams only. Let me show you. Okay, let me go ahead with further. So you can consider only one. So that is k equal to, if k equal to just 1, k equal to 1 in the sense, only 1 in the sense, so 2 power, so sorry, k equal to 0, 2 power 0, 2 into 0, that is 0, that equal to 1. So that is 1 by 1 chessboard. In 1 by 1 chessboard, if you consider whatever the chessboard it might be, so one tile must be always defective. So in our entire problem, the defective tile will be shown in full black color. The full black colored tile will be defective tile. So this is defective tile because we have only one tile with us. So this problem is already solved. So since this particular problem is already solved, then we have to consider that the T of, so here we'd like to consider k only, not n. So T of k will be equal to 0 because we did not put any triomino on this particular thing. We did not put anything. We did not place any triomino on this one because the size of your chessboard is 1 by 1. Only one tile will be there. So T of k will be equal to 0. Then secondly, if you consider this is 2 by 2, one more 2 by 2, one more t by 2, one more t by 2. So these are the 4 possibilities. So here defective will be available here. In this one, defective will be available here. In this one here. In this one here. So it is k will be equal to 1. K will be equal to 1. So 2 power. So 2 into 1. That is totally 4. So 4. What do you call? Tiles are there. Out of them, one tile will be defective. So therefore, one triomino. Three tiles are left over. So made up of these 3, we need one triomino. One triomino will be needed by us. So we have placed one triomino like this in such a way, otherwise like this in such a way, otherwise like this in such a way, otherwise like this in such a way. In these ways, you can place the triomino. So therefore, the problem will be solved. So therefore, either of these 4 problems, how many triominoes have been placed? How many triominoes have been placed? So exactly 1. If k will be equal to 1, so you could get the value as 1 here. The value as 1 here. Okay. Then, so we'll increase the size of the problem. So here k will be equal to 1, and here k will be equal to 0. Now we'd like to increase the size k equal to 2. So k equal to 2. So I'd like to give only 1 or 2 diagrams to you to understand, but it is not possible to give all 16 different kinds of diagrams here. 1 or 2 problems will be given. So here k will be equal to, in this particular thing, k will be equal to 2. So therefore, please, one moment, please. So now you could consider here 2 power 2 into 2, so minus 1. That is that will be equal to 2 power 2 into 2, 4, 16 minus 1. That is totally 15. You could observe this one here. You could observe this one here. So totally 15, one defective will be gone. There are 15 tiles which are non-defective tiles, which are very good defective tiles. Okay. Then how could you cover this? How could you able to cover this? Then how many number of triominos will be used to cover? So that is the point here. How many number of triominos will be used to cover here? Let me show you how this could be done by taking another color. Okay. So this is one particular possibility. This is the first triomino I would like to take into consideration. Okay, this is first triomino. And second triomino will be taken into consideration. This is the second triomino I would like to take into consideration to be filled with. This is second. This is second one. Let me draw some things here. Something like this. So this is first one and second one, something like this. And third one will be, I'd like to consider, so this is the third one, third triomino I'd like to place here. This is third triomino I would like to place here, the red one. And finally, so I'd like to take one more. This is fourth triomino I'd like to take into consideration to place. So this is the fourth triomino, the black one. And finally, so last and final triomino which I would like to consider is this one. So in this way you can place the triominos which you have defective, so at this particular place. Okay, the defective might be available anywhere else, not exactly the same position. Anywhere else the defective gets available here. Okay, in this way you can fill them. Okay, so like this, how many number of triominos are required? So triomino number 1, triomino number 2, triomino number 3, triomino number 4, and triomino number 5. 5 number of triominos are required to fill up this one here. Of course, but this is very huge problem. So because of huge problem, we just divide this particular problem into further, that is decompose this particular problem into further. So by taking something like this, let me show you. Okay, so one more example will be seems like this here. You can fill the triominos like anything here. So here also you can fill them in a particular order. There is no problem at all. Then how could you solve this particular problem? If 4 by 4 will be there with you, one defective tile will be there with you, then how could you solve this particular problem? Let me show you. Using diagrams, let me show you. So this is the way. So I'd like to divide this particular problem into further, that is 2 by 2, 2 by 2, 2 by 2. Look at this. This is first 2 by 2. This is second 2 by 2. This is third 2 by 2. This is fourth 2 by 2. Okay. So totally 4 sub problems have been come out. And what is our problem condition? The problem's condition is, so if you take any sub problem, if you take it is whole problem, there is no problem. One whole problem in the sense, if you could consider that this is so 4 by 4 kind of chessboard. Out of this 4 by 4 kind of chessboard, you have only one that is a defective, which has been mentioned here, and remaining 15 will be okay. They are so non-defective chessboards, non-defective tiles. And to solve this particular problem, what I am taking the first step? The first step is, let us divide this particular problem into further smaller. Smaller in the sense, so 4 2 by 2 number of chessboards will be taken. If you consider within this particular chessboard, it is okay. Within this particular 2 by 2, the first part of 2 by 2, so it is okay. This is okay. But if you consider in this particular part, on this particular part, on this particular plot, do you have any effective tiles? No. So within this particular part, in the sense, only this area. If you consider this particular 2 by 2, do you have any defective? No. If you don't have any defective, you cannot solve the problem. Because, so if you consider this particular area, only this particular area, so here it is 2 by 2, 2 by 2. So 2 by 2 must be having one defective tile, therefore you have three non-defective tiles, and if you have three with you, means number of non-defective tiles will be so 3 or 6 or something like that. That could be divided by 3 very successfully. Therefore, you can consider one triomino and can replace it. But here, within this particular part, you don't have any defective. Within this particular third part, you don't have any. This is fourth actually. Fourth part, you don't have any defective. You don't have any defective third part also. Then how could you solve this problem? This problem can be solved by introducing artificial defective tiles. By introducing artificial defectives. So those artificial defective could also frame, could also at the end of the problem, they are also supposed to frame a triomino. How that could be done? You can see. So this one is okay, and this one is non-defective. This one is non-defective. So this is non-defective. This is non-defective. This is non-defective, and this is non-defective. So the white color, I'd like to fill with the dark black. So this is defective for so this area. This is defective for this particular area. This is defective for this particular area. But they are supposed to be considered by us artificially, not exactly, artificially. Because the problem has been divided into so 4 2x2 chessboards. So that is why you have introduced. Then you have colored them, then you could identify. So this is actually defective chessboard. So then one triomino can be used to fill with the first number one, so 2x2, and another triomino will be filled with the second one, and another triomino has been filled with the third 2x2. Another triomino can be filled with the fourth 2x2. So whatever the artificial kind of defective triominos, defective tiles which you have been considered, they will be filled with some other color. They will be filled with some other color. If you eliminate this division, then you could understand this is the first triomino, this is second triomino, third triomino, fourth triomino, and this is fifth triomino. Yes, everything has been filled. Everything has been filled in a proper way. Therefore, so whatever the size of the chessboard it might be, if you have exactly one defective kind of tile will be available with you, then that could be always filled with the triominoes. Okay, so by showing this particular problem, you can understand in such a way. Then let me follow, or let me continue with the next slide. So 4x4 is gets over. Then what about 8x8? You can see 8x8. Okay, the solution could be occurred by if k equal to 0. So the problem is already solved. We have seen in the previous slides also. And then if k equal to 1, the problem will be very simple. That is, small of p will be gets to, so that one triomino can be used. And if k divide, if you have larger boards in the sense, so k will be greater than or equal to 2 will be there. Then you have to divide it into many number of pieces, just as I have shown in the just before slide, and so on. And if 8x8 will be there, okay, 8x8 will be there. So what is the problem here? You can see one more. If 8x8 problem will be there, then what exactly you can see? Look at this. This is 8x8, so chessboard, which is having totally 64 tiles are there. Out of 64 tiles, one particular tile is defective. Then what we are supposed to do? So we have to check that. First trick is we have to check that whether exactly one tile will be defective or not. Yes, it is. Then second one is that you have to divide so-called 8x8 into exactly 2 halves. How this could be? Like this, like this. If you do something like this, this is first 4x4, this is first 4x4, and this is second 4x4 1. So 4x4 2. This is 4x4 3. So this is 3, and this is 4 by 4. So 4 totally. So 64 tiles will be divided into in such a way. And there is one question just before we have seen in 4 by 4. There is one question. In this particular first 4 by 4 defective tile will be there. Doesn't matter. Then what about this? What about this 2? What about this 3? What about this 4? So look at this. There is no defective in this sub problem. Then will it be solvable by using divide and conquer? No. Every chessboard, whether it is whether it is so 4 by 4, 2 by 2, or 5 by 4, whatever the value it might be, then it must be always have one defective. So that I would like to artificially introduce some defective tiles in each and every. I mean, second one and the third one and fourth one. Look at this, how they can be done here. So here, so also you have to take care. After completion of this particular program, this particular problem, that particular completion must be framed. That artificially introduced so tiles must be framed here Triomino. You must remember that. You must always remember that. So therefore, so here, so this is defective, artificial defective for this particular. This is artificial defective for this particular thing, and this is artificial defective for this particular thing. Then, I don't know how to solve this 4 by 4. I couldn't understand how to solve this particular 4 by 4. Then how could you do? How could you solve this one? So follow the same step again. Divide this particular 4 by 4 into, so again 2 by 2 in such a way. After division, you can observe this particular 2 by 2. This 2 by 2 is okay. Then what about this 2 by 2, this 2 by 2? So therefore, I'd like to consider defective kind of artificial defective kind of so tiles in each and every 2 by 2. If you have 1 2 by 2, then you know how to fill them. Then I'll show you how to fill them. So in this way, it has been filled with the different colors. The pink color is artificially we have considered whatever the tiles we have considered as artificially so defective tiles, they are filled with pink color, and remaining everything will be filled with their own colors. Okay. Then you could get the answer such. Then you can combine. I have eliminated all black lines and red lines from this one. Therefore, so this is the solution for our problem. This is the final solution. Okay. Then, what is the algorithm? So this will be filled something like this. It is already in solved mode. It is 1 triomino can be used. But here it is 5 triominoes can be used, and we have to calculate how many triominoes could be used. Okay, 5 plus 5 plus 5 plus 5, 20 triominoes can be used to fill this particular so 8 by 8. Okay, then so let us consider so how the things will be. So I'd like to develop a particular algorithm for this one. Then you could get by using Python. I'd like to develop this one. So after developing this Python algorithm, I'd like to explain. So in some other time, okay, this algorithm. So it is somewhat difficult to understand. Explain to you. So that is why I'm left over this particular algorithm for a while, and I'll move to analysis. In general, 2 by 2 defective chessboard will be seems like this. 2 power k will be taken here in the sense 2 power k minus 1, 2 power k minus 1 is one block or one subproblem, another subproblem, another subproblem, another subproblem. 4 subproblems will be taken into consideration. Because of 4 subproblems, look at this. 2 power n equal to 2 power k, then t of k will be taken this much amount of so defective. Time taken will be 2 power k into 2 power k units of time. To take this one, t of k will be equal to 0 if n equal to 0. Otherwise, 4 into 2 k minus 1 plus c. C in the sense for comparison point of view. So 4 into t plus for t, k minus 1, because we have been taken, so k minus 1 number of subproblems will be taken into consideration. That is 4 t of k minus 1 plus c will be taken for otherwise. Sorry, here it is n. If n is k is not equal to 0. Then solve this particular problem. K of k equal to 4t into k of minus 1, and substitute the value of k minus 1 here. So 4 into 2 power k 2 power sorry 4 into 4t into k minus 2 plus c, that is the value of t of k minus 1, and elaborate this one. 4 square into t of k minus 2 plus 4c plus c, and substitute the value of k minus 2 value, that is 4t into k minus 3 plus c. That will be equal like this: 4 cube into t minus t of k minus 3 plus 4 square c plus 4c plus c. And if you continue this one for k number of iterations, then it is 4 power k into t of k minus k. K minus k will be equal to 0. So therefore, 4 power k minus 4 into c, k minus 2 into c, and so on. So 0 into anything will be get 0, so that you could have this particular so value will be taken into consideration, and this could be written 4k. Okay, this could be written 4k. So this is the evaluation. So defective chessboard problem will be given you. So big O of 4k, 4 power k. Okay. So 4 power k in the sense how many number of triominos you have been placed into the chessboard. That is the answer. Okay. So in this way, you can complete your so what is that defective chessboard problem. So go through this particular problem one more time. This video one more time, as you are not even even watching the videos what I am supposed to be placed into your group. I don't know why. So I hope that, I believe that if you are unable to watch those things, I will believe that yes, you people have understand what I am giving in this actual lecture. So it doesn't matter for me if you are supposed to go or go through. Yes, I have taken the attendance.